Type Ia supernovae are cosmic explosions so bright they can outshine entire galaxies, and yet they begin with something as small as a dying star stealing matter from its neighbour. What triggers these violent events, and why do they matter to our understanding of the universe? In this video we'll explore the science behind them. If you enjoy it, please like, subscribe and share, and tell us in the comments what fascinates you most about supernovae. Thank you for watching. Now let's begin. A white dwarf is the compact remnant left behind when a star of modest mass exhausts its fuel. Stars that begin life with less than about 8 times the mass of the Sun do not collapse into neutron stars or black holes. Instead, when their nuclear fuel runs out, they shed their outer layers, often as a glowing planetary nebula, while the core remains. This core becomes a white dwarf, a stellar object that is small, dense and unusual in its internal physics. In an ordinary star, the balance against gravity comes from thermal pressure created by nuclear reactions in the core. Hot gas pushes outward, counteracting the pull inward. In a white dwarf, however, nuclear fusion no longer occurs. Instead, the balance arises from electron degeneracy pressure. This phenomenon is a direct result of the Pauli exclusion principle in quantum mechanics, which states that no two electrons can occupy the same energy state simultaneously. When matter is compressed to the densities found in a white dwarf, electrons are forced into higher and higher energy states. The collective resistance of electrons to being squeezed further provides a powerful pressure that does not depend on temperature. This unusual form of pressure allows the white dwarf to be stable long after it stops shining brightly. Even as it cools, the star does not collapse because the degeneracy pressure remains. The structure of such a star is fundamentally different from a main sequence star. In its interior, carbon and oxygen nuclei are closely packed, forming what can be thought of as a dense lattice. Electrons move freely through this structure, filling available energy states up to a maximum level known as the Fermi energy. The result is an object with extraordinary density. A single cubic centimetre of white dwarf matter can weigh more than a ton. A cube of this matter, the size of a sugar lump, would outweigh a mountain on Earth. Although a white dwarf typically has a mass comparable to that of the Sun, its radius is similar to that of Earth. This contrast between mass and size is one of the defining features of white dwarfs. A remarkable property is that the more massive the white dwarf, the smaller its radius. Adding mass compresses the star further, because the stronger gravity requires an even greater electron pressure to balance it. Thus, the largest white dwarfs by mass are also the smallest in size. The surface of a white dwarf may retain thin shells of helium or hydrogen that were left behind when the progenitor star lost its outer layers. These shells are minuscule compared to the total mass, but they can play a role if the white dwarf resides in a binary system. Accretion from a companion star may begin through Roche-Lobe overflow or stellar winds, and the accreted matter often interacts with these surface layers. Cooling is the main evolution for a solitary white dwarf. With no internal fusion, it radiates away residual thermal energy slowly. Over billions of years, it dims and becomes more difficult to detect. Some of the oldest white dwarfs in the Milky Way are faint objects that give astronomers clues about the age of the galaxy. Eventually, the matter inside may crystallize, forming an immense solid structure at the atomic scale. The composition of white dwarfs varies depending on the mass and life cycle of the original star. The most common are carbon-oxygen white dwarfs produced by stars with initial masses similar to or a few times greater than the Sun. Oxygen-neon white dwarfs form from somewhat more massive stars where more advanced nuclear burning occurred before the star expelled its outer layers. Helium white dwarfs are also possible, though they usually arise in binary systems where mass loss prevented helium fusion from beginning. Each type shares the same fundamental support mechanism of electron degeneracy, but their chemical makeups affect their further evolution. The stability of white dwarfs is not absolute. Degeneracy pressure has a limit. The balance between gravity and this quantum pressure breaks down if the mass exceeds about 1.4 times that of the Sun. This value is known as the Chandrasekhar limit. It represents the maximum mass at which a white dwarf can remain stable. Below this limit, degeneracy pressure holds. Above it, the pressure cannot resist gravitational collapse. Although the Chandrasekhar limit is often discussed in connection with supernovae, it also defines the basic physical boundary for white dwarfs. A star that approaches this mass has a core density so high that carbon fusion may ignite. Unlike a normal star, the ignition is not regulated by expansion and cooling because degeneracy pressure does not respond to temperature. If burning begins, it can grow rapidly because there is no stabilizing feedback. For most white dwarfs, this situation never arises. Isolated remnants simply cool quietly over cosmic timescales. However, those in close binary systems can accumulate additional mass from a companion. As mass builds, the central density increases and the risk of runaway fusion becomes significant if the total mass approaches the critical threshold. Understanding the basic structure of a white dwarf therefore requires considering both its remarkable stability and its potential instability. At one level, it's a quiet, cooling remnant that can persist for billions of years. At another, it is an object balanced so delicately that external influences such as accretion may set the stage for catastrophic change. The discovery of white dwarfs in the early 20th century confirmed predictions from quantum mechanics about how matter behaves under extreme conditions. Observations showed stars of Earth-like size but solar-like mass, exactly as theory indicated. This unification of stellar astronomy with the new physics of quantum mechanics was one of the milestones in modern science. Today, the study of white dwarfs continues to inform astrophysics, not only for their role in stellar evolution, but also for the unusual events that can occur when they are pushed beyond their natural limits. White dwarfs are now understood as the final stage for the majority of stars in the galaxy. They fill the Milky Way by the hundreds of millions scattered remnants of earlier generations of stars. Each is small and faint yet profoundly dense. Their existence embodies the link between microscopic physics of electrons and macroscopic phenomena in the universe. Recognizing their properties is essential for understanding the later transformations that some of them undergo. The Chandrasekhar mass limit describes the maximum weight that a white dwarf can sustain before electron degeneracy pressure fails. This threshold, calculated in the early 20th century by the astrophysicist Subramanian Chandrasekhar, is about 1.4 times the mass of the Sun. The physics behind this limit comes from the nature of degenerate matter. In such matter, the electrons are pressed so tightly together that they provide outward pressure by occupying successively higher energy levels. As more mass is added, gravity compresses the star further, and the electrons are forced to higher energies. At some point, as the density grows, the electrons approach speeds comparable to the speed of light. When that relativistic condition occurs, the relationship between pressure and density changes. The degeneracy pressure no longer rises quickly enough to balance gravity. This is why there is an upper boundary for stability. The calculation of the Chandrasekhar limit required combining principles of quantum mechanics with special relativity. Quantum mechanics provided the rules for electron degeneracy, while relativity corrected the behavior of particles moving at extreme speeds. Chandrasekhar showed mathematically that there is no stable solution above a certain mass. The implication was profound: a white dwarf cannot grow indefinitely. Instead, once this threshold is approached, the star must either ignite nuclear reactions in a runaway fashion or collapse into a denser object such as a neutron star. For a carbon-oxygen white dwarf, reaching this limit means that central conditions become extreme. the density rises to billions of grams per cubic centimeter, and the temperature climbs to hundreds of millions of degrees. Under these conditions, carbon fusion reactions begin. In a normal star, nuclear burning would release energy, expand the gas, and reduce the temperature, slowing the reaction rate. This creates a stable balance between fusion and pressure. But in a degenerate star, the pressure does not depend on temperature. Heating does not cause expansion, so the nuclear reactions accelerate without a natural braking mechanism. This is the key pathway toward a thermonuclear explosion. The limit also explains the mass-radius relation of white dwarfs. A white dwarf with less mass has a larger radius, while one that is closer to the critical mass is smaller. At exactly the limit, the radius shrinks to zero. In theory, meaning the star cannot be stable at all. Observations confirm this inverse relation between size and mass in actual white dwarfs, reinforcing the theoretical result. Although 1.4 solar masses is the standard figure, the exact value of the Chandrasekhar limit depends slightly on composition. A carbon-oxygen white dwarf has a slightly different limit than an oxygen-neon white dwarf because the mass per electron is different. The equation of state for degenerate matter includes the ratio of nucleons to electrons, and that changes with chemical makeup. Thus, the number is often quoted as about 1.4, not an exact universal value. In astrophysics, the limit has become more than a boundary for white dwarfs. It is a dividing line in stellar evolution. Stars born with enough mass to leave cores above this threshold cannot end as white dwarfs. Instead, they collapse into neutron stars or black holes after supernova explosions of a different type. Stars that leave cores below the limit become white dwarfs. The importance of this number is that it sets the fate of stars and the conditions for the violent explosions associated with type Ia supernovae. When considering accreting white dwarfs in binary systems, the Chandrasekhar limit is central. A white dwarf that gains matter from a companion may inch closer to the limit over time. Each new layer of matter compresses the core slightly more. If accretion is steady, the star may reach central densities where carbon ignites. Because the star cannot expand in response to the rising temperature, burning races out of control. The entire star can undergo runaway fusion in seconds, releasing enough energy to unbind it completely. This process is one of the principal models for type Ia supernovae. The Chandrasekhar limit also provides an explanation for the uniformity of many observed type Ia events. Since the explosion occurs when the white dwarf mass is near the same value, the total amount of fuel available is similar from one event to another. The production of nickel-56, which powers the brightness of the supernova, through radioactive decay, is roughly consistent, leading to light curves that can be standardized. This is part of why type Ia supernovae are used as distance indicators in cosmology. Historical acceptance of the Chandrasekhar limit was not immediate. When Chandrasekhar first presented his findings, they were met with skepticism, even opposition from senior astronomers. The idea that nature imposes a strict upper boundary on stellar remnants was difficult to accept. Over time, however, evidence accumulated and the theory became established. The discovery of neutron stars and black holes later confirmed that stars above the limit cannot remain as white dwarfs. In practical terms, the limit is not a sharp dividing line in every case. Some white dwarfs may explode at slightly lower masses due to different ignition scenarios, such as the detonation of a helium shell. Others may merge with companions, producing conditions that differ from the classic near-Chandrasekhar model. Yet the concept remains the foundation. It defines the regime in which electron degeneracy can counter gravity, and the point beyond which it cannot. The limit also highlights the strange relationship between quantum rules on the microscopic scale and astronomical phenomena on the larger scales. The same principle that governs the arrangement of electrons in atoms determines whether a star the size of Earth can survive or explode. The Chandrasekhar mass is therefore more than just a number. It is the connection between the smallest particles and the fate of entire stellar systems. As white dwarfs approach this mass through accretion or merger, the precise way in which ignition occurs can vary. The limit itself simply marks the boundary where no static configuration is possible. Whether burning begins at the center or is triggered in outer layers depends on additional conditions. Nonetheless, the role of the Chandrasekhar mass in setting the stage is clear. It is the tipping point between long-term stability and catastrophic change. The composition of a white dwarf determines much of its eventual behavior, and the distinction between carbon-oxygen cores and oxygen-neon cores is important when considering which stars can become type we are supernovae. When a star similar to the Sun completes helium fusion in its core, the products are mostly carbon and oxygen. Such a star does not become hot enough to fuse these elements further. Instead, after it sheds its outer layers, the remaining dense core is a carbon-oxygen white dwarf. This is the most common type of white dwarf in the galaxy, and it is the standard starting point for many scenarios that lead to thermonuclear supernovae. Carbon-oxygen white dwarfs have masses typically around half to one solar mass, though they can be more massive. Their central densities are extremely high, and the matter is fully ionized, meaning nuclei and electrons are separated. The lattice of carbon and oxygen ions sits in a sea of degenerate electrons. Because the electrons provide most of the pressure support, the exact mixture of carbon and oxygen has only a modest effect on structure. However, it has a strong effect on the nuclear reactions that may ignite if the star is pushed toward instability. Carbon nuclei can fuse at somewhat lower temperatures than oxygen nuclei, so the presence of a large carbon fraction means ignition can occur at lower central conditions. Oxygen-neon white dwarfs form differently. They rise from stars more massive than those that leave carbon-oxygen remnants, but still below the threshold for core collapse supernovae. In such stars, the core burns carbon before the outer layers are lost, leaving behind oxygen and neon rather than carbon and oxygen. These oxygen-neon white dwarfs tend to be more massive on average. Their fate diverges from that of carbon-oxygen white dwarfs, because the fusion thresholds are different. Oxygen and neon require higher densities and temperatures to ignite. Instead of undergoing runaway carbon fusion, oxygen-neon cores may collapse into neutron stars when they approach the Chandrasekhar limit. This process is sometimes called an electron capture supernova, where the capture of electrons by nuclei reduces electron pressure and triggers collapse rather than explosion. The distinction between carbon-oxygen and oxygen-neon white dwarfs is therefore crucial. Carbon-oxygen white dwarfs are the primary progenitors for type Ia supernovae because they are able to ignite carbon explosively under degenerate conditions. Oxygen-neon white dwarfs, by contrast, are less likely to produce such explosions and more likely to undergo collapse. Observational evidence supports this distinction, as the spectra and yields of type Ia supernovae match models of carbon burning, rather than oxygen or neon burning. There are also helium white dwarfs, which form when stars lose their envelopes before helium fusion can begin. These remnants are usually of the lower mass, often less than half a solar mass. On their own helium, white dwarfs are not candidates for classical type Ia supernovae, but they can play a role in binary systems. If a helium white dwarf merges with a carbon-oxygen white dwarf, the helium can provide a surface layer that may ignite and trigger deeper burning in the carbon-oxygen star. This is one of the alternative pathways that has been proposed for sub-Chandrasekhar explosions, sometimes called double detonation models. The internal composition of white dwarfs has further implications for cooling. As they radiate away heat, their ions can crystallize, beginning in the center where the density is highest. Observations of white dwarf luminosity functions in star clusters indicate that crystallization is common in old remnants. The mixture of carbon and oxygen influences the crystallization process, as carbon-rich and oxygen-rich regions can separate during solidification, releasing latent heat that slows cooling. This phenomenon does not directly lead to supernovae, but it helps astronomers measure ages of stellar populations. Composition also affects the mass-radius relation and the precise value of the Chandrasekhar limit. A carbon-oxygen white dwarf has a slightly different limiting mass compared with an oxygen-neon one, due to differences in the ratio of nucleons to electrons. These details matter for theoretical models, but do not alter the broad outcome that only carbon-oxygen white dwarfs provide the right conditions for classical thermonuclear supernovae. From an observational perspective, distinguishing between these types of white dwarfs directly is challenging because they are faint and small. Astronomers infer their composition primarily from models of stellar evolution and from the properties of observed supernovae. The lack of neon-rich signatures in Type Ia spectra supports the conclusion that oxygen-neon progenitors are not dominant. In contrast, the production of intermediate mass elements such as silicon, sulfur, and calcium in Type Ia explosions matches the nucleosynthesis expected from carbon-oxygen burning. The pathway from stellar evolution to white dwarf composition is therefore central to understanding which stars can contribute to Type Y events. Stars like the Sun end quietly as carbon-oxygen white dwarfs that simply cool. If they happen to have a close companion, however, they may accrete material and grow in mass. In that situation, their carbon-rich cores make them candidates for runaway fusion. More massive stars that produce oxygen-neon remnants are far less likely to do so. Instead, they represent a different evolutionary route toward collapse. Thus, the chemical makeup of the white dwarf set long before it becomes a compact star dictates its ultimate destiny. The balance of carbon and oxygen, or oxygen and neon, determines whether the star may eventually explode or collapse. These differences show how initial stellar mass fusion pathways and late-stage evolution shape the population of white dwarfs and define which subset will later produce the events astronomers recognize as Type Ia supernovae. In a binary system where a white dwarf orbits a normal companion star, matter can flow from the companion onto the compact star. This pathway is known as the single degenerate accretion channel, and it represents one of the main scenarios by which a white dwarf may gain mass and approach instability. The mechanics of this mass transfer depend on the separation between the stars and the evolutionary state of the companion. If the companion star expands into a red giant, its outer layers may fill what is called the Roche lobe, the region of space where its gravity dominates. When that happens, gas flows through the inner Lagrange point and spirals toward the white dwarf. In other cases, winds from the companion may provide a steadier but less efficient supply of material. The material accreted onto the white dwarf is often hydrogen or helium from the outer layers of the companion. As it builds up on the white dwarf surface, it can undergo nuclear burning. If hydrogen is accreted at a slow enough rate, it may fuse steadily into helium, adding mass to the core of the white dwarf without much disturbance. If accretion is faster or less stable, hydrogen can accumulate until a thermonuclear flash occurs, leading to a nova eruption that ejects some of the material. These nova outbursts are spectacular, but usually do not destroy the white dwarf. Instead, the cycle can repeat many times. The long-term question is whether such a system can add enough mass to push the white dwarf toward the Chandrasekhar limit. Steady accretion is more favorable for growth than recurrent nova eruptions, since nova events remove mass as well as add it. Theoretical studies suggest that certain ranges of accretion rates permit stable hydrogen burning, which allows the white dwarf to increase in mass gradually. If the conditions are maintained, the star's mass can creep closer to the critical threshold, where central carbon ignition becomes unavoidable. This path is considered one of the classic channels for producing a Type Ia supernova. An important aspect of this channel is the role of helium. As hydrogen fuses into helium on the surface, helium may accumulate in a shell around the white dwarf. If conditions allow, this helium layer can also ignite. If the helium burning is stable, it simply adds mass. If it is unstable, it can cause helium flashes, which are similar in spirit to novae, but involve helium rather than hydrogen. Again, stability is key for allowing the white dwarf to grow rather than shedding material. Observations provide support for the single degenerate scenario in some cases. Systems known as super-soft X-ray sources are binaries in which a white dwarf accretes matter at a rate that produces steady nuclear burning on its surface. These systems shine in soft X-rays because the surface layers are extremely hot. They demonstrate that white dwarfs can indeed sustain stable surface burning under the right conditions, and such systems are considered strong candidates for future TPASS A events if mass growth continues. However, the efficiency of mass growth in these systems is still debated. Some researchers argue that winds and outbursts expel more material than is retained, making it difficult for the white dwarf to reach the Chandrasekhar limit. Others point out that the exact behavior depends on the balance of accretion rate, chemical composition, and binary dynamics. In either case, the process shows how delicate the balance is when a star attempts to cross the threshold from long-term stability to catastrophic runaway. Another complication is the possible presence of circumstellar matter around some Type Ia supernovae. If a white dwarf has been accreting heavily from a companion, one might expect signatures of expelled gas in the surrounding environment. In a few observed supernovae, hints of interaction with circumstellar material have been detected, such as narrow absorption lines that vary with time. These observations suggest that at least some Type Ia events may come from single degenerate systems where mass transfer has left a mark on the environment. Yet the evidence is not universal, and many Type Ia events lack such signatures. The single degenerate channel also offers a natural explanation for certain delay times between star formation and supernova occurrence. Because the progenitor requires a non-degenerate companion, the time until explosion depends on the evolution of that companion. This can be hundreds of millions to billions of years, consistent with the fact that Type Ia supernovae occur in both young and old stellar populations. Despite these supporting points, the single degenerate pathway is not the only explanation, and it may not account for the majority of observed events. Nevertheless, it remains a cornerstone of theoretical models because it shows how a white dwarf can, in principle, steadily approach the Chandrasekhar limit through accretion. The stability of hydrogen and helium burning on the surface, the efficiency of mass retention, and the presence of circumstellar gas all influence whether the path succeeds. From a structural perspective, the key outcome of this channel is a gradual increase in central density of the white dwarf. As mass builds, gravity compresses the core further. At some point, the conditions cross the threshold for carbon fusion. Because the white dwarf is degenerate, the initial ignition does not cause expansion and cooling. Instead, the burning accelerates, setting the stage for thermonuclear runaway. The details of that runaway depend on ignition geometry and flame propagation, but the single degenerate channel provides the environment in which this trigger can occur. The study of these systems continues with observations of cataclysmic variables, recurrent novae and super-soft sources, all of which may represent stages along the path. Each system provides clues about how mass transfer operates in real stars. By measuring their luminosities, spectra, and variability, astronomers attempt to determine how much mass is gained and lost. The answers are not yet final, but the principle remains clear. A white dwarf in a close binary has the potential to change its destiny through the steady, delicate flow of matter from its companion. Another important pathway toward a thermonuclear supernova involves the merger of two white dwarfs. This is called the double degenerate channel, and it differs from the single degenerate channel in that both stars are compact remnants. The process begins when two stars of comparable initial mass evolve together in a binary system. Each star sheds its outer layers and becomes a white dwarf. If the two remnants remain bound in a close orbit, they slowly lose orbital energy through the emission of gravitational waves. Over timescales of hundreds of millions to billions of years, the orbit shrinks until the two white dwarfs eventually come into contact and merge. The fate of such a merger depends strongly on the combined mass of the system and on how the mass transfer occurs when one star begins to disrupt. If the more massive white dwarf accretes material from the smaller one in a stable fashion, the mass can build up steadily, potentially pushing the combined object toward the Chandrasekhar limit. If the mass transfer is unstable, the smaller star may be torn apart rapidly, forming an accretion disk around the larger star. The disk then feeds mass inward, heating the outer layers of the surviving remnant and potentially triggering ignition. The double degenerate channel was proposed as an alternative to the single degenerate model to explain some observational puzzles. For instance, in many cases, astronomers do not detect evidence for a surviving non-degenerate companion after a Type Ia explosion. If both stars in the system are white dwarfs, there would be no such companion to detect. In addition, mergers are natural outcomes of binary evolution, and the rate at which close white dwarf pairs are observed in the galaxy is consistent with the frequency of Type Ia supernovae. A key issue in the double degenerate scenario is whether the merger leads to a thermonuclear explosion or to collapse into a neutron star. If the merger is too violent, the infalling material can heat the accretor so quickly that carbon ignition begins off-center, leading not to a global detonation, but to a slow burning that transforms the core into oxygen and neon. This outcome tends to drive the remnant toward collapse rather than explosion. On the other hand, if the accretion proceeds more gently, central ignition may occur, and runaway fusion can disrupt the entire star, producing a Type Ia supernova. The dynamics of merging white dwarfs are complex and are often studied with numerical simulations. These models account for orbital decay, tidal disruption, disk formation, angular momentum transport, and the ignition of nuclear burning. Results show that in some cases the merger can ignite carbon near the core in conditions suitable for explosion, while in other cases the remnant survives for some time as a massive, rapidly rotating white dwarf before eventually igniting. Observational evidence for the double degenerate channel comes from several directions. The discovery of double white dwarf systems with short orbital periods confirms that such pairs exist in nature. Some of these systems will merge within the age of the universe according to general relativity. Additionally, some Type Ia supernovae show no signs of hydrogen or helium from a companion star, supporting the idea that the progenitors may have been pairs of white dwarfs. The lack of circumstellar material in many events also fits this model. Gravitational wave astronomy adds a new dimension to this study. Space-based detectors planned for the future, such as the Laser Interferometer Space Antenna, are expected to detect the gravitational radiation from compact white dwarf binaries. Observing these systems directly will provide data on their numbers and merger rates, testing whether they can account for a significant fraction of Type Ia supernovae. One advantage of the double degenerate model is that it naturally explains events in older stellar populations. Since white dwarfs can persist for billions of years, their mergers can occur long after the stars were born. This is consistent with the fact that Type Ia supernovae occur in both young star-forming galaxies and in ancient elliptical galaxies where star formation has long ceased. However, challenges remain. The diversity of observed Type Ia light curves and spectra suggest that more than one progenitor pathway may be active. Some events may come from single degenerate systems, others from double degenerate mergers, and still others from variations such as sub-Chandrasekhar explosions. Untangling these contributions is an active area of research. Another subtlety is the possibility of double detonation in mergers. In some models, helium-rich layers on the merging white dwarfs ignite, first producing a surface detonation that sends a shock wave inward and triggers a deeper carbon detonation. This mechanism is one way to transform a merger into a successful supernova rather than a quiet collapse. Astronomers also examine the remnants of past supernova to infer progenitor channels. If no surviving companion is present in the debris field, the double degenerate model becomes more plausible for that event. Careful searches with space telescopes and large ground-based observatories have placed limits on possible survivors in nearby remnants, and in some cases the absence of such stars strengthens the double degenerate interpretation. The double degenerate channel highlights the role of orbital dynamics and gravitational wave losses in stellar evolution. It shows how binary systems can lead to outcomes very different from those of isolated stars. Instead of cooling quietly, a pair of white dwarfs can end in one of the most energetic explosions in the universe. Whether this occurs depends on the mass ratio, the speed of mass, transfer the role of rotation, and the timing of nuclear ignition. Each of these factors is still under investigation, but together they provide a coherent picture of how two dead stars can, through their interaction, give rise to new light. When a white dwarf grows close to the critical mass where instability becomes unavoidable, the conditions in its interior change in ways that set the stage for carbon ignition. At the very center, densities climb to billions of grams per cubic centimeter. Temperatures also increase into the range of several 100 million degrees. At these values, carbon nuclei can fuse. In an ordinary non-degenerate star such as a main sequence or giant star, nuclear reactions that increase the temperature would cause the material to expand. Expansion reduces the density and temperature, creating a stabilizing feedback that regulates burning. In a white dwarf supported by electron degeneracy pressure, this mechanism does not operate. The pressure comes from quantum rules, not thermal motion, so heating alone does not relieve the pressure or cause expansion. As a result, once fusion reactions start, they do not self-regulate. Instead, they intensify. The first stage of ignition often begins with localized regions in the core. Small patches may ignite carbon fusion and form hotspots. These hotspots can grow and link together, but whether they combine into a global flame front depends on details of turbulence and convection. If ignition is distributed throughout the center, the burning may resemble a central flame. If it begins off-center or in multiple regions, the flame geometry can be more complex. Regardless of the exact location, the initial burning starts as a subsonic process known as a deflagration. In a deflagration, the flame front advances through thermal conduction and turbulent mixing, slower than the speed of sound, but still extremely fast on astrophysical timescales. As the deflagration grows, it releases energy and drives convection. The rising hot material moves outward, mixing with cooler surrounding regions. Some models suggest that the entire white dwarf can undergo a convective simmering phase, lasting hundreds to thousands of years before the runaway becomes unstoppable. During this time, the burning is weak but spreads. This simmering gradually changes the composition by producing isotopes of neon magnesium and other intermediate elements. This pre-explosion simmering also sets the stage for how the flame will behave when it fully ignites. Once the burning becomes dynamic, the energy release is enormous. The core cannot expand quickly enough to relieve the pressure because degeneracy persists. The burning accelerates and the flame front begins to race outward. If the process remains a pure deflagration, the star may not be fully disrupted. In some theoretical models, a pure deflagration leaves behind a remnant while ejecting only part of the mass. Such outcomes are sometimes invoked to explain peculiar low-luminosity events. In the standard picture for a classical Type Ia supernova, the deflagration does not remain subsonic. Instead, it undergoes a transition into a detonation, a supersonic burning front. This transformation is called the deflagration to detonation transition. The physics behind this transition is still uncertain, and is one of the most active research areas in supernova theory. Turbulence may wrinkle the flame, creating conditions where local shockwaves form. These shocks can ignite regions explosively, transforming the slow flame into a fast detonation that sweeps through the star in seconds. If a detonation occurs, the consequences are dramatic. The detonation consumes the white dwarf almost completely, releasing about 10 to the 44 joules of energy, enough to unbind the star entirely. The burning synthesizes new elements, particularly nickel-56, which later decays to cobalt-56 and then to iron-56. The distribution of these products depends on the density of the material when it burns. At the highest densities near the core, the burning favors iron peak elements. At lower densities further out, intermediate mass elements such as silicon and sulfur dominate. This layering produces the chemical structure that later reveals itself in observed spectra. The ignition process is therefore the crucial turning point. A white dwarf that has cooled in quiet stability for billions of years can suddenly, in less than a second, ignite in a chain reaction that destroys it. The path from simmering to runaway, from deflagration to detonation, is controlled by details that cannot be seen directly, but must be inferred from the light of distant explosions. This challenge drives the reliance on multidimensional simulations, which attempt to capture turbulence, convection, and flame physics at scales from the size of the star down to microscopic structures. Some models also consider whether ignition might occur off-center or in multiple sparks. If ignition begins away from the core, the flame may buoyantly rise toward the surface before burning the entire star. The outcome in such cases can differ from central ignition, producing different ratios of elements and different observational signatures. The geometry of ignition remains one of the least constrained aspects of the process, yet it has a profound effect on the appearance of the resulting supernova. The timescales involved are striking. For thousands or even millions of years, the white dwarf may accrete slowly, its core changing only gradually. Then, once the ignition threshold is crossed, the entire star can be destroyed in seconds. The transition from stability to catastrophe demonstrates how narrow the boundary is between support by quantum pressure and runaway thermonuclear energy release. Observations provide indirect support for the ignition picture. Light curves and spectra show the products expected from carbon fusion under degenerate conditions. Early light curve behavior suggests that in some cases the burning begins deep and spreads outward, consistent with central ignition. Peculiar events, by contrast, may hint at incomplete burning or alternative ignition geometries. No direct observation of the ignition exists, but the overall theoretical framework is consistent with the diversity of data. The central ignition of carbon in a degenerate core is thus the defining event that converts a white dwarf into a Type Ia supernova. It represents the moment when the balance maintained for billions of years collapses and nuclear physics takes over. The study of this process continues to refine how astronomers interpret the light from distant galaxies and how they trace the story of matter under the most extreme conditions. When carbon ignition begins in the dense interior of a white dwarf, the form of the burning determines whether the star is only partially disrupted or completely destroyed. Two distinct regimes of thermonuclear flame propagation exist: deflagration and detonation. In a deflagration, the flame front moves subsonically, carried forward by the diffusion of heat and by turbulent mixing. In a detonation, the flame front races ahead supersonically, driven by shock waves that compress and heat unburned fuel, igniting it almost instantly. Both regimes are central to the theory of Type Ia supernovae. The physics of a deflagration begins with conduction. Carbon nuclei fuse in the hot region, releasing energy that heats the adjacent layers. This heat raises the temperature until fusion ignites in those neighboring regions as well. The flame moves slowly compared to sound waves, and in the dense white dwarf interior, turbulence strongly influences its speed and shape. Convection and rising plumes wrinkle the flame front, increasing its surface area and accelerating the burning. Yet even when turbulent, a deflagration remains subsonic. Because the star cannot expand in response to heating, the process still runs away, but not with the explosive power of a detonation. A pure deflagration can in theory disrupt a white dwarf. However, in many models, it does not release enough energy to completely unbind the star. Instead, it ejects part of the material, while leaving behind a bound remnant. Observationally, this scenario has been linked to a peculiar class of events known as Type Ix supernovae. These are less luminous than classical Type Ia events, and show spectra consistent with incomplete burning. The idea that a pure deflagration produces such outcomes illustrates how the mode of flame propagation shapes the diversity of observed explosions. In contrast, a detonation front advances supersonically, typically at thousands of kilometers per second. Shock waves from the burning region compress unburned material ahead, heating it to fusion temperatures. The reaction zone moves so rapidly that the entire star can be consumed in less than a second. The energy released is sufficient to overcome the binding energy of the white dwarf, unbinding it completely. A detonation therefore leads to the full disruption that characterizes normal Type Ia supernovae. The major theoretical challenge is explaining how a deflagration, which is the natural mode of initial ignition, can transform into a detonation. This process is called the deflagration to detonation transition. The physics is not yet fully understood, but several mechanisms are proposed. One possibility is that turbulence stretches and distorts the flame until localized regions compress strongly enough to ignite detonations. Another idea is that colliding plumes of hot ash create shocks that converge and trigger supersonic burning. Numerical simulations show that such transitions can occur under plausible conditions, but the exact details remain uncertain. The outcome of this transition has direct consequences for nucleosynthesis. A deflagration burns material at relatively low densities, producing more intermediate mass elements like silicon, sulfur, and calcium. A detonation burning at high densities produces more iron peak elements like nickel and iron. The layered chemical structure inferred from observed spectra suggests that both processes may occur in sequence: an initial deflagration that transitions to a detonation. This combination allows the explosion to produce both the intermediate mass elements seen in spectra and the large amounts of nickel-56 that power the light curve. Observational evidence supports the idea of mixed burning modes. Early-time spectra of Type Ia supernovae show strong features from silicon indicating the presence of intermediate mass elements. Later spectra show the dominance of iron peak elements consistent with deeper layers burned under detonation-like conditions. The coexistence of both signatures implies that no single regime explains the explosion. Instead, a hybrid picture involving both deflagration and detonation fits the data. The geometry of flame propagation adds another layer of complexity. In three-dimensional simulations, the flame front does not advance smoothly. Instead, it bubbles, stretches, and collides with itself. Different ignition points can produce asymmetric burning, which may leave subtle imprints on observed spectra and light curves. Polarization measurements of some type Weyr supernovae reveal low but non-zero asymmetry, consistent with such turbulent flame structures. These observations remind astronomers that the explosions are not perfectly spherical, even if they are relatively uniform compared to other types of supernovae. The timescale of flame propagation is extremely short. Once the deflagration has transitioned into detonation, the entire white dwarf can be consumed in about 1 second. Energy release is so immense that the star's binding energy is overcome, and the ejecta expand at thousands of kilometers per second. From the slow simmering that may last thousands of years before runaway ignition, the system suddenly evolves into total disruption within the blink of an eye on a cosmic timescale. The distinction between deflagration and detonation also explains the diversity of observed events. Some faint supernovae may represent failed or incomplete transitions where deflagration dominated. Some extremely bright events may involve conditions that favored extensive detonation and higher nickel yields. By examining spectra and light curves, astronomers can infer the balance between these burning modes in individual explosions. The study of flame propagation in white dwarfs continues to push the limits of computational astrophysics. Simulations must resolve both global scales of thousands of kilometers and microphysical processes of flame thicknesses that can be less than a centimeter. No single simulation can yet capture every detail, so researchers use approximations to connect small-scale physics with large-scale outcomes. Despite these challenges, progress has been steady, and models now reproduce many of the observed properties of Type Ia explosions. Understanding the difference between deflagration and detonation, and the transition between them, is fundamental to the science of Type Ia supernovae. It determines how the star is destroyed, what elements are created, and how the explosion appears to distant observers. Though uncertainties remain, the combined evidence from theory, simulation, and observation points to a complex but coherent picture where both modes of burning play a role. The balance between them is what shapes the final outcome of each event. While the near Chandrasekhar mass scenario with central ignition has long been the standard picture for Type Ia supernovae, alternative models propose that explosions can occur in white dwarfs of lower mass. One of the leading alternatives is the sub-Chandrasekhar double detonation model. In this scenario, the white dwarf does not need to approach the Chandrasekhar limit to explode. Instead, the trigger comes from a layer of helium on its surface. If enough helium accumulates in a shell, conditions can cause the helium to detonate. The detonation in the helium layer sends shock waves into the core, compressing and heating the carbon-oxygen material beneath. This secondary ignition can then set off a carbon detonation in the interior, disrupting the star even though it is below the critical mass. The process begins with a white dwarf accreting helium-rich material from a companion star. The companion may be a helium star or another white dwarf that provides helium. As the helium builds up on the surface, pressure and temperature rise. At a certain point, the base of the helium layer becomes hot and dense enough to ignite fusion. Because the helium is degenerate, the ignition is unstable and rapid, leading to a detonation in the shell. This shell detonation alone would not produce a typical Type Ia event. However, the shock waves that travel inward from the shell can converge in the core and trigger a secondary detonation of carbon. This double detonation, first in the helium shell, then in the carbon core, destroys the white dwarf and releases the energy seen in a supernova. One of the strengths of the double detonation model is that it allows for a broader range of progenitor systems. White dwarfs of less than the Chandrasekhar mass are far more common than those close to the limit. If sub-Chandrasekhar explosions can account for a significant fraction of Type Ia events, then the frequency of supernovae in the universe is easier to explain. Population synthesis studies support this possibility by showing that binaries capable of transferring helium are numerous enough to match observed rates. The double detonation model also makes predictions about nuclear synthesis and spectra. The helium shell detonation produces heavy elements in the outer layers of the ejecta, including radioactive isotopes and intermediate mass elements. If the shell is thick, the products may create strong spectral lines that are not observed in most normal Type Ia events. For this reason, early versions of the model were considered problematic. However, later refinements showed that thinner helium shells can still trigger the core without leaving strong signatures. These thinner shells may produce only subtle effects in spectra, consistent with the diversity observed in real events. The carbon core detonation in the double detonation model proceeds similarly to the central detonation in the Chandrasekhar mass case, producing nickel-56 and iron peak elements in the center, and silicon, sulfur and calcium in intermediate layers. The presence of helium shell ashes in the outer ejecta may explain some peculiar spectral features seen in certain supernovae. In particular, some fast-rising faint Type Ia events may be the result of explosions with relatively thick helium shells. Observational tests of the double detonation scenario focus on early time light curves and spectra. The first few days after explosion can reveal signatures of surface composition. Ultraviolet and optical observations sometimes show excess blue light or unusual absorption features that could come from helium shell products. A handful of supernovae have shown hints of such features, lending support to the idea that at least some Type A events arise from this mechanism. The diversity of Type Ia supernovae also fits naturally with the double detonation picture. If the shell mass varies, the explosion properties change. A thicker shell produces more surface products and a fainter event. A thinner shell produces a brighter event more similar to normal Type Ia explosions. In this way, the model provides a framework for understanding both the common and the unusual members of the Type Ia family. Another advantage of the sub-Chandrasekhar model is its ability to explain supernovae in environments where massive white dwarfs may be less common. Since white dwarfs below the Chandrasekhar mass are plentiful, explosions from these stars could occur in both young and old populations. This matches the observed distribution of Type Ia supernovae across many types of galaxies. Despite these strengths, uncertainties remain. The physics of helium ignition is complex, and the exact conditions for detonation depend on temperature, density, and shell mass. Multidimensional simulations are required to determine whether shocks from the helium detonation can consistently ignite the carbon core, while models show that it is possible the robustness of the mechanism is still under study. In addition, direct observational evidence for helium in the outer layers of normal Type Ia supernovae is limited. Nonetheless, the double detonation model continues to gain support as a viable alternative or complementary pathway. Rather than replacing the Chandrasekhar mass scenario entirely, it may contribute a significant fraction of observed events. The relative importance of the two channels is still debated, but it is increasingly clear that multiple pathways likely coexist. In summary, the sub-Chandrasekhar double detonation model illustrates how a white dwarf can explode without ever reaching the traditional mass limit. By using a surface helium shell as a trigger, the star can be destroyed while still below the Chandrasekhar mass. This idea expands the range of possible progenitor systems, helps explain observed diversity, and provides a framework for linking peculiar spectral features to specific physical conditions. It underscores the theme that in the lives of white dwarfs, small variations in environment and composition can determine whether they fade quietly or end in a sudden and total disruption. Once ignition begins and runaway fusion spreads through a white dwarf, the nuclear reactions that unfold determine what new elements are created. This process is known as nucleosynthesis. In a type Ia supernova, the burning of carbon and oxygen under degenerate conditions produces both radioactive isotopes and stable elements that fill the ejector with new matter. The sequence of reactions begins when carbon nuclei fuse into heavier nuclei such as neon sodium and magnesium. As temperatures rise above 1 billion degrees, oxygen fusion also contributes. The reactions proceed rapidly, moving material toward intermediate mass elements like silicon, sulfur, and calcium. At the highest densities near the center, where burning is most complete, the matter reaches nuclear statistical equilibrium. In this state, the relative abundances of nuclei are set by balance among reactions, and the products are primarily iron group elements, especially nickel-56. Nickel-56 plays a central role because it is unstable. It decays with a half-life of about 6 days into cobalt-56, releasing gamma rays and positrons. Cobalt-56 itself is also unstable with a half-life of about 77 days and decays into stable iron-56. These decays provide the energy that powers the light of the supernova long after the initial explosion. Without radioactive nickel, the bright light curve of a Type Ia event would fade far more quickly. The amount of nickel produced varies from event to event, but is typically around half a solar mass. Brighter supernovae generally correspond to those with larger nickel yields. The layering of elements in the ejector reflects the density at which different regions burned. The inner regions, where the densities were highest and burning was most complete, are rich in iron group elements. Surrounding them are shells of intermediate mass elements like silicon and sulfur. The outermost layers may contain unburned carbon and oxygen if the flame did not consume every part of the star. This layered structure is observed in spectra, where absorption lines of silicon and calcium appear in the early days, and iron lines dominate at later times. The distribution of isotopes also depends on whether burning proceeded by deflagration detonation or a combination of both. A pure deflagration tends to produce less nickel and leave behind more unburned material, while a detonation at high densities produces more nickel and iron. The combination of an initial deflagration followed by detonation gives yields that match the observed ratios of intermediate and iron group elements in most normal type supernovae. Nucleosynthesis in type Ia explosions is a major source of iron in the universe, while core collapse supernovae contribute to the synthesis of many elements. Type Ia supernovae dominate the production of iron and iron group elements in galaxies. This has been confirmed by studies of chemical evolution, which show that the gradual enrichment of galaxies with iron over billions of years matches the expected contribution from Type Ia explosions. Stars that formed early in galactic history contain little iron, while younger stars born after many Type Ia events are richer in iron. Intermediate mass elements such as silicon and calcium, also made in these explosions, provide key observational diagnostics. The silicon-2 absorption line at 6,150 angstroms is one of the defining spectral features used to identify Type Ia supernovae. Calcium and sulfur lines also appear prominently. These features confirm that the burning did not produce only iron group elements, but also stopped partway in some regions as expected from layered burning. Gamma-ray observations provide another test of nucleosynthesis. The decay of nickel and cobalt produces gamma rays that can sometimes be detected directly in nearby events. For example, observations of supernova 2014J with gamma-ray telescopes detected lines from cobalt decay, confirming that radioactive nickel was present in the quantities predicted by models. Such measurements are difficult because the sources are faint and far away, but they represent direct evidence of the isotopes created in the explosion. The exact yields of nucleosynthesis depend on many factors: the density profile of the white dwarf at ignition, the flame propagation mode, and the initial composition. A carbon-rich white dwarf produces slightly different ratios than one with more oxygen. Metallicities in the progenitor star also affect trace element production. Researchers use large nuclear reaction networks in simulations to follow thousands of possible reaction pathways and predict the final isotopic abundances. Comparing these predictions with observed spectra and galactic chemical abundances helps refine the models. The energy released by nucleosynthesis is enormous. Converting carbon and oxygen into nickel and other heavy elements releases about 10 to the 44 joules, comparable to the total energy radiated by the Sun over its entire lifetime. Most of this energy goes into kinetic motion, driving the ejector outward at thousands of kilometers per second. A fraction, however, appears as light powered by radioactive decay. This balance explains why Type Ia supernovae are not only luminous, but also have characteristic timescales for brightening and fading. In addition to iron group and intermediate mass elements, trace amounts of other isotopes are produced. These include stable isotopes of nickel and cobalt, as well as elements like titanium and chromium. Although present in smaller quantities, they can leave signatures in late-time spectra. By analysing these faint lines, astronomers can probe conditions deep in the ejector and constrain details of the explosion. Nucleosynthesis also connects Type Ia supernovae to cosmic evolution. The iron in the Earth's core, the nickel in terrestrial minerals, and much of the iron in blood hemoglobin all ultimately trace back to thermonuclear explosions of white dwarfs. This connection is not the focus of supernova studies in a technical sense, but it illustrates the large-scale importance of these events for enriching the universe with heavy elements. The study of nucleosynthesis in Type Ia supernovae remains active. Researchers continue to refine the nuclear reaction rates, test the influence of flame turbulence on yields, and compare predictions with observed abundances in galaxies. Although the broad outline is clear that carbon and oxygen burn to nickel, cobalt, and iron, with intermediate elements in outer layers, the fine details still hold uncertainties. Each new observed supernova provides additional data to test these models, ensuring that the picture of nucleosynthesis continues to sharpen. The violent release of energy in a Type Ia supernova not only synthesizes new elements, but also sets the conditions for how the explosion shines. The observed brightness of these events is shaped by radiation transport, the movement of photons through the expanding ejector. At the moment of explosion, most of the energy is stored in the kinetic motion of the ejector and in the radioactive isotopes created during nucleosynthesis. The ejecta expand at thousands of kilometers per second, and as they expand, their density drops. Photons generated by the radioactive decay of nickel-56 into cobalt-56 and then into iron-56 slowly diffuse outward. This diffusion, along with absorption and scattering in the layers of ejecta, controls the shape of the light curve. At early times, the ejecta are dense and opaque. Gamma rays from the decay of nickel are absorbed close to their source, and their energy is thermalized, heating the surrounding material. This heat is then re-radiated at optical wavelengths, producing the visible brightness of the supernova. As the ejecta expand and thin, photons can escape more easily. The light curve rises to a peak as radioactive heating builds up, then gradually declines as the amount of nickel decreases and the ejecta become more transparent. The characteristic timescale for the peak is set by the diffusion time of photons through the ejecta, which depends on both the mass of the ejecta and its opacity. The peak luminosity of a Type Ia supernova is therefore tied directly to the amount of nickel 56 synthesized in the explosion. Events that produce more nickel shine more brightly, while those with less nickel are fainter. This explains the observed correlation between brightness and decline rate. Brighter supernovae decline more slowly because their higher nickel content continues to provide heating over a longer period. Fainter events decline more quickly. This relationship, known as the Phillips relation, underlies the use of type Ia supernovae as standard candles for measuring cosmic distances. Color evolution also reveals the physics of radiation transport. In the days after peak brightness, the supernova appears blue because the ejecta are hot. As time passes and the ejecta cool, the emission shifts toward redder wavelengths. Spectra show absorption, features from ions such as silicon, sulfur, and calcium, which evolve as the ejecta expand and ionization states change. Early spectra often display a prominent absorption line from singly ionized silicon at a wavelength of 6,150 angstroms. This feature is one of the hallmarks of type Ia classification. Its strength and velocity provide information about the temperature and expansion speed of the ejecta. The silicon feature also demonstrates how layered nucleosynthesis reveals itself in spectra. Intermediate mass elements like silicon reside in outer layers, so their absorption dominates at early times when the photosphere is still within those layers. As the photosphere recedes deeper into the ejecta with expansion, iron group elements begin to dominate and spectra become rich in iron lines. By the nebula phase several months after explosion, the ejecta are so thin that photons escape freely, and emission lines from forbidden transitions of iron and cobalt emerge. These late-time spectra provide direct evidence of the radioactive isotopes created in the explosion. Radiation transport models attempt to reproduce these observed features by solving equations that track the propagation of photons through expanding, scattering, and absorbing gas. The challenge lies in the complexity of the problem. Opacities depend on millions of atomic transitions, and the geometry of the ejecta can be asymmetric. Simplified models use assumptions such as spherical symmetry and averaged opacities, while advanced simulations incorporate multidimensional structures and detailed atomic physics. Both approaches are necessary to compare theoretical yields with observed light curves and spectra. Gamma-ray escape plays a central role in shaping the decline of the light curve. At first, nearly all gamma rays deposit their energy locally, but as the ejecta expand, a larger fraction escapes without interaction. This reduces the heating rate, causing the light curve to fade more quickly. Observations of late-time decline rates confirm this effect, showing that the slope matches the radioactive decay of cobalt when the ejecta are still opaque, then steepens as transparency increases. Polarization studies provide additional insight. If the ejecta were perfectly spherical and homogeneous, scattered light would show little polarization. In reality, some type Ia supernovae exhibit low but detectable polarization, indicating mild asymmetries in the ejecta. These asymmetries may reflect the ignition geometry or turbulence in the flame, and they are consistent with multidimensional models that show non-uniform distributions of burning products. The velocity of the ejecta is another diagnostic. Absorption features in spectra shift due to the Doppler effect, allowing astronomers to measure expansion speeds. Typical velocities for silicon lines are about 10,000 km per second near maximum light, with variations from event to event. The breadth of spectral lines also reflects the velocity distribution. By comparing these features with radiation transport models, researchers constrain the density and composition profiles of the ejecta. The connection between radioactive decay and brightness has been tested by direct detection of gamma rays from nearby supernovae. Observations of supernova 2014J with gamma-ray instruments detected lines from cobalt decay matching predictions from nickel-powered models. These detections confirm the central role of radioactive heating in type Ia light curves. They also provide measurements of nickel mass, allowing direct comparison with light curve estimates. Radiation transport is thus the bridge between the microphysics of nuclear burning and the macroscopic observation of supernova light. The layered structure of ejecta, the decay chain of nickel and cobalt, and the diffusion of photons all combine to shape the light curves and spectra. Each observed feature carries information about the explosion's conditions. By interpreting these signals, astronomers reconstruct events that occur billions of light-years away and understand the physics of white dwarfs destroyed in seconds. The steady and predictable behavior of type Ia supernova light curves, despite variations in detail, is what makes them so valuable for cosmology. Their uniformity arises from the fundamental link between nickel production and brightness, and from the physics of radiation transport in expanding ejecta. Even small variations can be corrected by empirical relations, enabling these explosions to serve as tools for measuring the expansion of the universe. The usefulness of type Ia supernovae as distance indicators arises from their consistent relation between brightness and decline rate. In the early 1990s, astronomer Mark Phillips showed that brighter events fade more slowly, while fainter ones decline more quickly. This empirical correlation, now called the Phillips relation, allows astronomers to standardize type Ia supernovae as so-called standard candles. A standard candle is an object whose intrinsic luminosity is known, so that by comparing its apparent brightness with the expected value, the distance can be measured. Type Ia supernovae are not all identical, but the Phillips relation provides a way to correct for variations and bring them onto a common scale. The practical method involves measuring the light curve of each supernova in detail. The shape of the light curve, including how quickly it rises and how steeply it falls, carries information about the nickel mass produced and the diffusion of photons through the ejecta. By fitting the observed light curve to templates that include the stretch factor, which accounts for the timescale of evolution, astronomers can determine the intrinsic brightness. Color corrections are also applied to adjust for reddening by dust and for differences in temperature evolution. After these corrections, the scatter in brightness among type Ia events is reduced to a level small enough to make them excellent distance indicators. This standardization has been tested across many events in different galaxies and environments. The results show that once corrected, type Ia supernovae have a nearly uniform luminosity. This uniformity allows them to serve as cosmological probes out to distances of billions of light-years. Their extreme brightness visible across the observable universe makes them invaluable for mapping cosmic expansion. The use of type Ia supernova for cosmology has had profound consequences. In the late 1990s, two independent teams measured the distances to supernovae at high redshifts and compared them with their redshift velocities. The results showed that distant supernovae appeared dimmer than expected in a universe slowing down under gravity. The interpretation was that the expansion of the universe is accelerating, driven by a component now called dark energy. This discovery, awarded the Nobel Prize in Physics in 2011, relied critically on the reliability of type Ia supernovae as standardized candles. To ensure accuracy, many observational campaigns have been devoted to improving calibration. These include nearby surveys that provide well-observed light curves for anchoring the relation, and distant surveys that extend the measurements to higher redshifts. Instruments in both ground-based observatories and space telescopes contribute, and cross-calibration between different photometric systems is essential. Any systematic error in brightness calibration translates directly into errors in distance, and thus in cosmological conclusions. Dust is one of the main sources of uncertainty. Dust in the host galaxy or along the line of sight can dim and redden the light from a supernova. Correcting for this requires knowledge of the reddening law, which describes how dust absorbs different wavelengths. Observations show that the dust properties in some host galaxies differ from those in the Milky Way, complicating corrections. By analyzing colors and spectra, astronomers attempt to disentangle intrinsic variations from dust effects. This remains an active area of refinement in supernova cosmology. Another source of systematic uncertainty comes from the environments of the host galaxies. Studies suggest that the average brightness of standardized type Ia supernova depends slightly on host galaxy properties, such as stellar mass star formation rate and metallicity. Incorporating these environmental factors into calibration improves consistency. It also highlights that while the explosions are broadly similar, small differences in progenitor composition and environment can influence details of the light curve. Despite these complexities, the Phillips relation and its extensions remain remarkably robust. The scatter in standardized luminosities is small enough to measure cosmological distances with percent-level precision. This makes type Ia supernovae one of the pillars of observational cosmology, alongside the cosmic microwave background and baryon acoustic oscillations. Each method provides complementary information, but supernovae remain the most direct tracers of the expansion history. The concept of stretch and color corrections is central to this process. The stretch factor adjusts for differences in the width of the light curve, while color corrections account for both dust reddening and intrinsic color differences. Together, they bring a diverse population of explosions onto a common scale. The effectiveness of this approach has been demonstrated repeatedly in large surveys, which show that corrected type Ia supernovae align on a consistent Hubble diagram, a plot of distance versus redshift. The calibration process also requires linking nearby and distant samples. Nearby supernovae can be observed with high precision and serve as anchors. Distant supernovae observed with larger uncertainties extend the measurement to earlier cosmic times. By connecting, the two astronomers trace how expansion has changed over billions of years. This is how the evidence for accelerated expansion first emerged, and it continues to be refined with new data. The application of type Ia supernovae to cosmology illustrates how a detailed understanding of microphysics such as nickel decay and radiation transport translates into measurements of the universe at the largest scales. The chain from white dwarf structure to thermonuclear burning, to light curve shape to distance measurement is long but coherent. Each link must be secure for the method to be reliable. Ongoing work continues to test each step, but the overall framework has proven sound. In summary, the Phillips relation and the standardization of type Ia supernovae transform them from catastrophic stellar deaths into precision tools for cosmology. Their brightness, uniformity, and predictable behavior allow astronomers to chart the expansion of the universe, to detect the influence of dark energy, and to refine cosmological parameters. The reliability of these explosions as distance indicators rests on careful corrections, extensive surveys, and a deep understanding of both their astrophysical mechanisms and their observational signatures. Observing type Ia supernovae requires coordinated strategies because they evolve quickly, changing brightness and spectral features over days to weeks. Time domain surveys are the foundation of discovery. These surveys repeatedly scan large areas of the sky, comparing images taken at different times to detect new sources of light. When a supernova appears, it brightens rapidly, so catching it early provides valuable information about its rise and peak. Modern surveys use wide-field telescopes equipped with sensitive digital detectors to monitor millions of galaxies. Automated software searches for transient events and follow-up observations then confirm the nature of each candidate. Early discovery is particularly important because the first few days after explosion may carry signatures of the progenitor system and ignition conditions. Some events show an initial flash of light that could be caused by interaction between the supernova ejector and a companion star, or by the presence of a thin outer shell of material. Detecting such features requires observations within hours of explosion, which is challenging but increasingly possible with continuous surveys and automated alerts. Space-based telescopes and networks of robotic ground-based observatories are now able to respond quickly, capturing the earliest stages of the light curve. Spectroscopy provides the most direct insight into the composition and velocity structure of the ejector. Early-time spectra reveal absorption lines from intermediate mass elements like silicon, sulfur, and calcium. The velocities inferred from these lines are around 10,000 kilometers per second, a measure of the expansion speed. As the supernova evolves, spectra change, showing different ionization states and eventually ion group elements as the ejector thin. By collecting spectra at multiple times, astronomers construct a detailed timeline of the explosion, mapping how the layers of material are revealed over time. Polarization measurements add another dimension. Light scattering in a perfectly spherical distribution would cancel out polarization, but any asymmetry produces a small net polarization signal. Observations of Type Ia supernovae generally show low polarization consistent with mostly spherical explosions, but with small departures. These small asymmetries support theoretical models that involve turbulent ignition and multidimensional flame propagation rather than perfectly uniform burning. The level of polarization varies from event to event, hinting that progenitor systems and ignition geometries are not all the same. Late-time spectra obtained months after explosion, when the ejector, a transparent probe, the innermost regions. These nebula spectra display emission lines from forbidden transitions of iron and cobalt. Their relative strengths and shapes provide estimates of nickel mass and the distribution of radioactive isotopes. As the ejector expand further, gamma rays and positrons from cobalt decay escape more directly, and the decline rate of the light curve reflects the radioactive decay chain. Comparing observed decline rates with theoretical expectations provides another test of nucleosynthesis models. Gamma-ray observations, though technically difficult, supply direct evidence of radioactive decay. Instruments capable of detecting high-energy photons have captured emission from cobalt decay in nearby supernova, confirming that the light curves are powered by nickel decay as predicted. These measurements are rare because of the faintness of the sources, but they are among the most direct pieces of evidence linking explosion physics to observed light. In addition to direct observation of supernovae, astronomers study remnants of past events. Supernova remnants such as Tycho's supernova of 1672 and Kepler's supernova of 1604 still expand as shells of hot gas and dust. X-ray observations of these remnants reveal elemental abundances consistent with Type Ia nucleosynthesis, such as strong iron emission. The structure of the remnants also provides clues to the explosion geometry and the surrounding environment. By comparing models with observations, researchers can constrain which progenitor channels are most likely for historical events. Time-domain astronomy has advanced rapidly with new facilities. The Zwicky Transient Facility, for example, scans the sky every night, discovering thousands of supernovae each year. The upcoming Vera C. Rubin Observatory, with its legacy survey of space and time, will extend this capability, detecting even more distant and earlier events. These facilities, combined with rapid follow-up, will vastly expand the sample of Type Ia supernovae and allow detailed statistical studies of their diversity. Another method involves searching for companion stars in the aftermath of explosions. If the single degenerate channel is correct for some events, the companion star should survive the explosion, possibly with a high velocity or unusual chemical composition. Astronomers have searched for such survivors in the centers of nearby supernova remnants. In some cases, no obvious candidate has been found supporting the double degenerate model. In other cases, stars with unusual properties remain under study. This line of investigation continues to test competing progenitor scenarios. Multi-wavelength observations enrich the picture further. Optical light curves are the most common, but infrared observations reveal features less affected by dust extinction. Ultraviolet spectra probe the outermost layers of ejecta, sensitive to composition and metallicity. X-ray and radio observations can detect interaction between the ejecta and circumstellar material. The presence or absence of such interaction helps distinguish between progenitor models, since single degenerate systems may leave more circumstellar gas than double degenerate systems. The integration of all these observational methods, time domain, discovery spectroscopy, polarization, gamma ray detection, remnant studies, and multi-wavelength coverage creates a comprehensive view of type Ia supernovae. Each method provides different constraints, and together they build a consistent but nuanced picture. The key lesson is that while type Ia supernovae are broadly uniform, they also display diversity. Some are brighter, some are fainter, some show peculiar spectra, and some reveal signs of interaction with their surroundings. Understanding this diversity requires both detailed observations of individual events and large statistical samples to reveal patterns. Ultimately, observational methods serve to test and refine theoretical models. The timing of the light curve, the velocities of spectral lines, the symmetry of polarization, and the elemental abundances in remnants all feed back into simulations of ignition and burning. By matching data with models, astronomers move closer to resolving the remaining uncertainties about progenitors and explosion mechanisms. The progress of this field illustrates the power of combining technology theory and careful observation to unravel phenomena that occur at cosmic distances, yet are governed by the physics of atomic nuclei and quantum mechanics. Although type Ia supernovae share common features that make them valuable as distance indicators, they are not all identical. Diversity within the class is significant, and understanding this variation is central to building a full picture of their origins. Normal events follow the expected light curve, spectral signatures, and nickel yields. But numerous peculiar subtypes exist, ranging from unusually faint to unusually bright explosions. Each subtype provides clues about alternative pathways and ignition conditions. One prominent category of faint events is the group often called type IX supernovae. These explosions are less luminous than typical type Ia events, sometimes by several magnitudes. Their spectra show iron features but weaker silicon lines, and their ejecta velocities are lower. Many models suggest that they result from pure deflagration without a transition to detonation. In such a scenario, the burning is incomplete and part of the white dwarf may remain bound as a remnant. This outcome produces less nickel-56 and therefore a fainter light curve. The existence of IX events indicates that not all white dwarfs are fully destroyed when they ignite. At the opposite extreme are unusually bright supernovae, sometimes described as super-Chandrasekhar candidates. These events appear to require more nickel than a near-Chandrasekhar mass white dwarf can produce. Their broad light curves and high luminosities suggest ejecta masses above the traditional limit. One possible explanation is that they come from the merger of two white dwarfs with combined mass exceeding the Chandrasekhar limit. Rapid rotation or strong magnetic fields may also allow stability at higher masses before ignition. These events are rare, but their existence challenges the idea that all type Ia explosions occur at roughly the same mass. Another peculiar group shows strong interaction with surrounding material. In these cases, the ejecta collide with dense circumstellar gas, producing narrow emission lines and additional luminosity from shock heating. These interacting Type Ia supernovae blur the line between thermonuclear and core collapse categories, since they resemble hydrogen-rich Type IIn explosions in some respects. The presence of circumstellar material points to a single degenerate progenitor with substantial mass loss before the explosion. Such cases demonstrate that progenitor systems can leave significant imprints on the immediate environment. Some events also show unusual spectral features or color evolution that set them apart from normal Type Ia supernovae. For example, peculiar objects like SN 2002CX and its relatives combine faint luminosity with low ejecta velocities and distinctive spectra. Others display strong titanium features or early ultraviolet excesses. These variations may correspond to differences in ignition geometry, shell masses in double detonation models, or composition differences due to progenitor metallicity. Statistical studies of large samples confirm that diversity is real and structured. Brighter events with slow decline rates tend to occur in younger star-forming galaxies, while fainter, faster declining events are more common in older stellar populations. This environmental dependence suggests that progenitor age and metallicity influence the explosion properties. The correlation strengthens the view that multiple progenitor channels contribute to the observed population. The range of observed luminosities also affects the calibration of Type Ia supernovae for cosmology. The Phillips relation corrects much of the variation, but peculiar events must often be excluded from cosmological samples. For example, IAX explosions and super-Chandrasekhar candidates do not follow the standard relation and could bias distance estimates if included. Distinguishing normal from peculiar events requires good spectroscopy and light curve coverage, emphasizing the importance of comprehensive observational programs. Another dimension of diversity involves asymmetry. Some supernovae show higher polarization or velocity gradients in their spectral lines, pointing to less spherical ejecta. These may reflect differences in ignition points or flame propagation. While most events are broadly symmetric, small departures can account for subtle differences in brightness and color. Multidimensional simulations predict such asymmetries, and observational evidence supports their presence. The variety of outcomes highlights the complexity of ignition physics. A white dwarf may ignite at different locations, may undergo deflagration, detonation, or both, and may accrete mass at different rates. Each combination produces different yields, light curves, and spectra. The observed diversity therefore encodes information about the distribution of initial conditions in progenitor systems. Decoding this information remains one of the major challenges in supernova research. Rare subclasses remind astronomers not to generalize too strongly from the majority. The discovery of unusual events often stimulates new theoretical models. For example, the identification of IAX supernovae spurred the development of partial deflagration models. The observation of very luminous events led to renewed interest in double degenerate mergers and rotational support. Interacting events revived consideration of mass loss in single degenerate systems. Each peculiar case adds a new piece to the puzzle of how white dwarfs can explode. Despite this diversity, the core idea remains that all these events involve thermonuclear runaway in a degenerate white dwarf. The differences lie in how ignition is triggered, how burning proceeds, and how the progenitor system evolved beforehand. Diversity does not undermine the utility of Type Ia supernovae for cosmology, but does require careful classification and correction. It also enriches understanding of stellar evolution by showing the range of possible outcomes when compact remnants interact and ignite. In conclusion, the diversity and subtypes of Type Ia supernova demonstrate that nature uses multiple pathways to achieve thermonuclear explosions. Normal events dominate and provide reliable distance indicators, but faint IX explosions, bright super-Chandrasekhar candidates, and interacting events reveal the breadth of possibilities. Studying this diversity deepens knowledge of ignition physics binary evolution and the role of environment while ensuring that cosmological applications remain robust. The variety of observed explosions reflects the complexity of stars and binaries, and it ensures that research on Type Ia supernovae continues to evolve. To connect observed supernovae with theoretical models, astronomers rely heavily on computer simulations. Modeling a Type Ia explosion is a formidable task because it involves many physical processes across a huge range of scales. At the heart of the problem is multidimensional hydrodynamics. The ignition of carbon fusion begins at points a few kilometers across, while the star itself spans thousands of kilometers. Turbulent convection stirs the core on intermediate scales, creating a highly complex flow pattern. To capture this, simulations must solve equations of fluid dynamics under conditions of extreme density and temperature, often in 3 dimensions. These models show how initial sparks of burning grow into flame bubbles, how turbulence wrinkles the flame front, and how buoyant plumes rise and merge. Alongside fluid dynamics, nuclear reaction networks are essential. Carbon and oxygen fusion proceeds through chains of reactions involving dozens or hundreds of isotopes. Each reaction releases energy, alters composition, and affects the progress of the flame. Reaction networks calculate the abundances of nickel, cobalt, iron, silicon, sulfur, and other elements. Because following every isotope is computationally expensive, many simulations use reduced networks that approximate the main energy release. Later, post-processing with larger networks refines the predicted yields. These outputs are compared with observed spectra and light curves to test whether the model produces the right mix of intermediate mass and iron group elements. Radiative transfer adds another critical layer. The explosion produces hot expanding ejecta that scatter and absorb photons. Simulating how light emerges requires solving equations of radiation transport through material with varying opacity. Millions of atomic lines contribute to absorption and emission. Approximations are necessary, but sophisticated codes now simulate spectra and light curves with increasing accuracy. These radiative transfer calculations translate the internal state of the model into observable quantities, making direct comparison with data possible. One of the main challenges is the deflagration to detonation transition. Simulations of pure deflagration often fail to match the brightness and chemical layering of normal Type Ia events. Pure detonation, by contrast, burns too much material to iron group elements and produces too little silicon. The hybrid picture, where deflagration transitions into detonation, reproduces both the nickel yield and the intermediate mass elements seen in observations. But the exact conditions for the transition remain uncertain. Researchers test different ignition geometries, turbulence intensities, and flame models to see how often detonations occur. Despite progress, no consensus exists on the precise mechanism. Another challenge lies in the initial conditions. Real white dwarfs are not perfectly uniform spheres. They may rotate, have magnetic fields, or contain composition gradients left from their progenitor stars. The location and number of ignition points in the core are unknown. Simulations therefore explore a range of possibilities. Some begin with many ignition sparks spread through the core, others with a single off-center spark. The outcome varies. Some cases yield bright explosions, others faint events or failed detonations. This variety mirrors the diversity seen in real supernovae, suggesting that ignition geometry is a key factor. 3-dimensional simulations reveal asymmetries that 2-dimensional models cannot. Flame plumes rise, collide, and wrap around the star. detonation fronts curve and interact. The result is ejecta with chemical inhomogeneities and velocity variations. Observations of small asymmetries in polarization and spectral line profiles are consistent with these predictions. Thus, multidimensional modeling is essential for understanding both the typical uniformity and the subtle departures from symmetry in type Ia events. Computational limits remain a constraint. Resolving the true flame thickness, which can be less than a centimeter across a star thousands of kilometers wide, is impossible with current resources. Instead, models use subgrid prescriptions to approximate small-scale flame behavior. Different prescriptions lead to different outcomes, adding uncertainty. Increasing computing power and improved algorithms gradually reduce these uncertainties, but they cannot yet eliminate them. Despite the difficulties, simulations have achieved notable successes. They reproduce the general light curve shapes and spectral sequences of normal type Ia supernovae. They predict nickel yields consistent with observations and explain the presence of intermediate mass elements at outer layers. They also account for the range of luminosities and decline rates by varying ignition conditions and progenitor masses. In this way, models provide a framework that connects microphysics with cosmic observations. Uncertainties, however, are far from resolved. The fraction of type Ia supernovae that come from near-Chandrasekhar mass explosions versus sub-Chandrasekhar double detonations remains debated. The conditions for deflagration to detonation transitions are not fully understood. The role of helium shell detonations in triggering explosions is still being explored, and the influence of progenitor metallicity on yields is not precisely quantified. Each of these factors contributes to diversity and affects how reliably supernovae can be standardized for cosmology. Observational advances feed directly back into modeling. Early light curve data constrain ignition locations, gamma-ray detections test, nickel yields and remnant abundances test, long-term nucleosynthesis predictions. As new surveys deliver larger samples with earlier discovery models can be tested with increasing rigor. At the same time, improvements in computing allow more detailed simulations, including rotation magnetic fields and complex flame physics. The modeling of type Ia supernovae therefore represents an iterative cycle between theory and observation. Observations reveal diversity, asymmetry, and subtle variations. Models attempt to reproduce them, suggesting new diagnostics. Those diagnostics then guide further observations. This process has steadily improved understanding over decades, though key questions remain open. The balance between deflagration and detonation, the role of sub-Chandrasekhar explosions, and the diversity of progenitor channels are all subjects of continuing investigation. In the end, modelling efforts show that while type Ia supernovae are broadly consistent with thermonuclear disruption of carbon-oxygen white dwarfs, the precise path varies. Multidimensional hydrodynamics turbulence, nuclear reaction, networks and radiation transport all play indispensable roles. The complexity of these models reflects the complexity of nature itself, where microscopic quantum processes and large-scale fluid flows combine to produce some of the most powerful explosions in the universe. Even with decades of study, important uncertainties remain in the science of type Ia supernovae. These uncertainties begin with the progenitor systems themselves. Whether most explosions arise from single degenerate systems, where a white dwarf accretes from a normal companion, or from double degenerate systems where two white dwarfs merge, is still unresolved. Observations provide evidence for both channels. Some supernovae show hints of circumstellar material consistent with mass transfer from a companion, while others show no such signs and fit more naturally with mergers. The lack of a surviving companion in many well-studied remnants suggests that double degenerate systems may contribute significantly, but the exact fraction from each pathway is unknown. Ignition geometry is another area of uncertainty. The conditions under which carbon ignites in a near Chandrasekhar mass white dwarf are complex. Models suggest that ignition may occur at multiple points or off-center, but no direct observation can confirm this. The geometry of ignition affects how the flame develops, how quickly it transitions from deflagration to detonation, and how the resulting ejecta are distributed. Slight differences in ignition geometry can lead to large differences in brightness and spectra. This sensitivity makes it difficult to predict outcomes with precision. The mechanism of the deflagration to detonation transition remains perhaps the most significant unresolved problem. While hybrid models involving both burning modes match many observations, the physical trigger for transition is not well understood. Turbulent mixing shock collisions or acoustic instabilities have all been proposed, but no definitive explanation has emerged. The difficulty lies in the tiny scales at which the transition must occur compared to the size of the star. Direct simulation of the relevant microphysics is beyond current computational ability, so approximations are necessary. These approximations may or may not capture the true physics. Sub-Chandrasekhar double detonation models add further complexity. Thin helium shells may trigger explosions consistent with many normal Type Ia events, but whether such shells exist in real systems is uncertain. If helium shells are too thick, they produce observable spectral signatures not seen in most events. If they are too thin, they may not ignite carbon effectively. Determining the prevalence of conditions suitable for double detonation requires more detailed understanding of binary evolution, helium accretion, and surface ignition physics. Metallicity of the progenitor stars also introduces uncertainty. The initial chemical composition affects both the likelihood of explosion and the yields of nucleosynthesis. Higher metallicity increases the abundance of isotopes like neon-22, which can alter reaction pathways and reduce the production of nickel-56. This in turn affects the brightness of the supernova. Observations show some correlation between host galaxy metallicity and standardized luminosity, but the trend is not yet fully quantified. Understanding how metallicity shapes explosions is essential for ensuring that Type Ia supernovae remain reliable distance indicators across cosmic history. Another area of debate concerns the diversity of observed events. While normal Type Ia supernovae can be standardized, peculiar subclasses complicate the picture. Type IX events, Super Chandrasekhar candidates and interacting events may each represent different physical mechanisms. The relative frequency of these subclasses is not well established, and their contribution to chemical enrichment of galaxies may differ from that of normal events. Models must account not only for typical explosions but also for this diversity, explaining how different conditions lead to different outcomes. Late-time behavior of supernovae also raises questions. Observations months to years after explosion probe the innermost ejecta and the efficiency of gamma-ray trapping. Some events show faster declines than expected, suggesting variations in density or clumping of material. Others show unusual emission features that imply asymmetries or additional sources of energy. These late-time diagnostics are valuable but difficult to obtain because of the faintness of the sources. They remain a frontier in constraining models. The rate of Type Ia supernovae across cosmic time is another uncertainty. Observations show that rates vary with galaxy-type star formation history and redshift. Theoretical models of binary evolution attempt to reproduce these trends, but often disagree on the relative contribution of prompt explosions which occur soon after star formation and delayed explosions which occur billions of years later. The balance between these populations affects both cosmology and galactic chemical evolution. Determining the delay time distribution requires larger samples and more detailed modeling of binary populations. Even the role of magnetic fields and rotation in white dwarfs is not fully understood. Rapid rotation can increase the effective Chandrasekhar mass by providing additional support, potentially allowing more massive white dwarfs to exist before exploding. Magnetic fields can channel accretion flows and affect flame propagation. Yet these factors are difficult to measure directly and remain speculative in many models. Despite all these uncertainties, progress continues steadily. Each new supernova observed provides additional constraints. Surveys discover thousands of events each year, revealing statistical patterns and rare outliers alike. Advances in computational astrophysics allow more realistic simulations of multidimensional flames and complex binary evolution. Gamma-ray detections, polarization measurements, and nebula spectra all add new pieces to the puzzle. Though no single model yet explains every observation, and the overall framework of thermonuclear runaway and degenerate white dwarfs remains robust. The science of Type Ia supernovae is therefore a mixture of consensus and open questions. Consensus holds that the explosions involve carbon-oxygen white dwarfs, disrupted by runaway fusion. Consensus also holds that nickel-56 powers the light curves, that silicon absorption defines the class, and that the Phillips relation enables standardization. The open questions concern the relative importance of different progenitor channels, the ignition geometry, the detonation mechanism, and the detailed influence of environment. These are the active frontiers where future research is directed. As long as uncertainties remain, cosmological applications must be handled with care. Systematic effects from progenitor diversity, metallicity dependence, and dust corrections could bias measurements of dark energy, if not properly accounted for. Astronomers continue to refine calibration methods, expand samples and test models to ensure reliability. The combination of theory, observation, and simulation aims to close the gaps in understanding. In the end, Type Ia supernovae embody both clarity and mystery. Their basic mechanism is understood, but their details remain elusive. Their light curves are uniform enough to map the cosmos, yet their progenitors are still debated. This tension drives ongoing work, ensuring that the study of these explosions will remain central to astrophysics for years to come.